This week's discussion is about statistical analysis of associations dealing with correlation. Now, correlation is going to be a key word throughout this lecture, and let's learn a little bit more. The first thing you'll notice right here is we have the outline of what we'll be covering. So here in the outline, you can see the different topics throughout this lecture, which we'll go through most of. So let's go to why are we doing this and how are we going to visualize this? So the motivation behind this is we want to analyze the relationship between two numeric quantities. And that's probably one of the biggest notes you need to take, is that correlation is a specific kind of association between two numeric quantities. If you don't have a quantitative x and a quantitative y, you are not doing correlation. So you could analyze something like gender as an x variable and height as a y variable, and that would be an association between the two variables, but it would not be a correlation. You must have something like height and weight, or like in the examples here with sports analytics, have something like fumbles and wins, which are both quantitative. Think about it. More fumbles, probably less wins. You can kind of do this if something's positive, they'll follow each other, or they could decrease with each other, like less fumbles for the Vols, less wins for the Vols. Or wait a minute, less fumbles for the Vols, more wins. That's a negative correlation when they go in opposite directions. But if you said something like less passing yards, less wins, that's also positive because more passing yards, more wins. So when they follow each other in the quantitative direction upwards, it's a positive correlation. When they go in opposite directions, it's a negative correlation. Lots of examples to talk about here, especially if you go to education, like people's college GPA, when we look at their high school GPA, are probably positively correlated, as in if one goes up, the other tends to be higher too. It doesn't cause the other to go higher, but we just see an association where people with high school GPAs generally have higher college GPAs. Additionally, we've got marketing analytics right here and customer analytics. So you can look at something when Trader Joe's is trying to open its store, it might look at the sales at Shoney's, because maybe the sales at Shoney's explains why there's certain sales at Trader Joe's. Remember from X and Y, figuring out which variable is which, X is the explanatory variable and Y is the one we're interested in, hence the variable of interest. So we can use this concept of correlation to understand two quantitative variables and see if they have an association between them. Now remember, two quantities are associated for whatever reason, knowing one quantity would give you information about another quantity. So let's say you were to know somebody's height. Like I'm 6'3", so would you have a guess of my weight? Now you might not know it exactly, but knowing I'm 6'3" would narrow down the possible values. If you're 6'3", you're probably more than 100 pounds, you might be around 200-ish. What if I told you my nephew is about 4'8", I think right now? Well, you might have a guess or narrow down on his weight. So with this, we know that there's an association, and in this instance, a correlation between the two quantitative values. And I just want to reiterate again that all correlations are associations. As in, like if I say something's correlated, that is a specific type of association. But not all associations are correlations. That's because an association is just when X and Y have a relationship. But when X and Y are both quantitative, that relationship, association, is specifically called a correlation in some senses, especially in the linear sense, which we'll be getting into more here shortly. So the first thing we want to do is visualize this correlation. So let's take a look what's going on right here. You'll notice X is quantitative along the number line, and Y is quantitative. Now, what you can see is, at the value of 10, we can narrow down the quantities of Y, and they're generally lower. So at the higher value of X, 17, the distribution over here shows that there is a higher kind of mean to the values. So typically, at X17, the values of Y are typically higher, right about there. At X15, the values of Y are typically moderate. And at X10, the values of Y over here on the scale are typically a little bit lower. And it doesn't mean if we're at X17, it'll be high, because we could be at this point here, and at X10, we could be at this point here. But it does kind of narrow down the values, and we would say that there's a positive relationship here that for higher values of x, we typically see higher values of y, and this is a positive correlation, which is a type of association. So remember these 3 steps right here, which we'll be using throughout this lecture. The first step is going to be visualizing the relationship with a scatter plot. A scatter plot is going to be the bivariate visualization of 2 quantitative variables. Remember, a scatter plot is the bivariate visualization of 2 quantitative variables, which is what you saw on the previous slide when you saw the dots on the screen with an x and a y-axis. When you have a scatter plot, you want to use with your eyes right here and take a look at what's going on. Just look at it and see what's going on there. A little eyeball right there looking at it, and you can see it kind of goes upwards, kind of has a linear trajectory to it. You might even see some outliers. But we're going to make a scatter plot, look at it, and then we're going to gauge statistical significance. Now, statistical significance merely means something is unlikely by random chance, or would occur by random chance less than 5% of the time. Random chance would look like the following. It's just if we put random dots across this XY axis. So if someone told me these dots were just randomly spread out, I would say, no, that doesn't look likely by random chance. That looks unlikely by random chance. Hence, this has a low p-value, and this has a high p-value. We'll talk more towards the end about using the permutation procedure to get an exact p-value, but the bottom plot on the screen is one that is likely by random chance, and the top plot on the screen is one that is unlikely by random chance, even with the outlier, i.e., the plot up top has a lower p-value, unlikely by random chance, and the plot down below would have a higher p-value, more likely by random chance. This plot right here, does it look likely by random chance? What do you see? Well, step 1 was to make the visualization. So you see right here we have the score on the midterm, which is a quantitative x, and the score on the final, which is a quantitative y. Notice that there is a positive trajectory with minimum outliers that go against the relationship, and it looks to me like the spread of the points around it are somewhat similar. So I'd say this looks like there's a relationship. Seems like people who score higher on the midterm generally score higher on the final. And a key aspect of what we're going to do here in this lecture is we're going to do a little bit of lecturing, and then we're going to go do the work in R. So take a look at the file we have over here, and let's do a little work in R. Okay, so we've got some code already written for us. Let's take a look at the first step right here on line 1, which is to load library reg class. Now, library reg class calls the reg class library. If you've already installed reg class or have it running, there'll be no problem with running this code. Make sure you've installed reg class. Data survey 10 pulls the data from the reg class library. And you can notice this here when I type survey 10 is inside of reg class library. When I run this, the data will appear in the global environment, which is kind of the brain of R where it knows everything. Now we're going to use 2 vectors here. These are quantitative vectors, and you can actually look at the quantitative vectors by opening it here and taking a look at the data set and seeing a preview of it. The height and weight vector are both quantitative vectors, and we can print them to the screen. This means right here the 694th person was 72 inches tall, and right now the 694th person was 175 pounds. Now we get to an important code that we'll use for the remainder of this lecture. We have here associate. The associate function is in reg class and lets us look at the association between an x and y variable. The way it goes is y tilde x comma data equals. And that's kind of the base format of it. So you have 2 arguments that are kind of necessary. Argument 1 is a formula. Think of it as like y equals x. That's not an equals though, that is a tilde. The tilde is the button on your keyboard next to the number 1 over there on the far side. So y tilde x for the formula, y tilde x, and then data equals is the data frame it's in. So think about this. We want to explain somebody's weight, or excuse me, explain somebody's height, y. Somebody has a height, and use weight to explain it, and the data is inside of survey 10. I wouldn't put the $signs here. Some people do that. It causes a bit of an issue with some of the code. This is the best way to code it here that causes usually no errors. So when we run this, we're going to get a lot of output. We're only going to talk about a little bit of it right now, but let's take a look. The first thing you'll notice is that the plot didn't turn out so pretty. sometimes you might have to increase your plot window to get a better looking plot. So let's remake it so we don't get the error down here with plot.new figure too large for window. Now when we remake it, it actually adds the permutation histograms below. We're going to zoom in on this graphic over here and just talk about it. This is a scatter plot with border histograms. Notice that we see a positive trajectory that is mostly linear. It starts to level out towards the end. It is also monotonic. We'll be reviewing these words shortly. And there are some outliers on the far side. We also have border histograms showing us the distribution of weight. Looks like the centrality of weight is towards about 140, 150. And then we have a histogram for height, which the central part of that data is about at 68. So there are some outliers down there, and it's more unimodal symmetric with some low outliers. And this one's a little bit more right skewed because it's pulled to the high side. So remember, the first step here, which we're just covering right now, is to look at the scatter plot, and what do you see? I see some outliers. I see a mostly positive, somewhat linear trajectory, and maybe it has a low p-value. More on that in a little bit. Let's go back to the notes. So here we are with some of those terms we just mentioned. Strength, direction, form, unusual features will be covered right now. So when it comes to direction, there are really two directions: positive, negative. And there's kind of neither. Think about these points right here. Well, they go up, positive. They go down, negative. They still go up. Even if it curves, they still go up, positive. This is kind of neither or mix, because it doesn't really go up or down. You could say that. You could say, well, it kind of goes up and then it goes down. And that's a fine way of describing it, but it's not really one strong direction. So you really only have positive, negative, or not really either direction, or you could say a mix of directions. The next thing we have right here is the form. And there's going to be two types of form in this class. We have something that is a line or not a line. And we have things that are monotonic or not monotonic. So line's the easy one. Does it follow a line? Yeah, that follows a line. A line mostly goes through the data, and the data mostly goes around the line. Does that follow a line? Yeah, data mostly goes through the line. Does this one? Look there towards the end. I'd say there's some non-linearity towards this one. How about this one? No way, no how is that linear. So a line or linear is just putting a line through the data and seeing if it follows it. So is it linear, mostly linear, not too linear? You tell me. Now, where people usually get stuck is monotonic versus non-monotonic. And when we have things that are monotonic go in one direction. As in this data here goes in one direction. It goes up. This data goes up and then down, so it's non-monotonic, not going in just one direction. This data right here, which I'm drawing, is going in one direction, even though it starts to slope at the bottom. It's what we call a sigmoidal shape, S-shape to the data. And so a sigmoidal S-shape like that is monotonic down. It has a direction of down, it's nonlinear, and it's monotonic because it's going mostly down at all times. It never really goes back up. So monotonic is when the points go in one direction. Think of your favorite band, One Direction, monotonic. Still listen to that? I don't know. So we have monotonic and also linear as the types of form. And when it comes to strength, strength is going to be the vertical scatter. What do I mean by vertical scatter? Well, if you were to draw bands as we have here on the screen, how tight are those bands? Now, the thing to remember is strength is not form. As in, this is not linear, and this is linear. But the one over here is stronger, and this is moderate. So that's a strong relationship, and this is a moderate, and this is a weak. And it really doesn't have any good form to it. It's kind of a non-existent weak relationship, where the second one is a linear, positive, moderately strong relationship. And the third one is going to be a kind of sigmoidal. There's a sigmoidal for you, but it's also nonlinear. Probably best to just say nonlinear. It is monotonic because it goes up at all times. And it's very strong because the points are tight around the form. So remember, strength has nothing to do with form, other than it's how tight it is around the form. But the form will not dictate the strength. It's the tightness of the points around the form that dictates the strength. So the more vertical scatter there is, the weaker. The weakest relationship you can have is going to be one like this. and this is what we would expect to see by random chance right here, and this would have a correlation equal to 0, and that's where we're going here in a moment. So here we are with the last two terms right here, strength, direction, form, unusual features. For unusual features, we have outliers and heteroskedasticity. Sounds like a big word. Outliers is the easy one, so let's go there first. Outliers are going to be things that are far away from the bivariate relationship. That's a weird kind of negative relationship with a few outliers that venture away from the centrality of the data. This one right here has maybe some outliers or maybe a heteroskedastic relationship. Heteroskedastic means hetero, different, skedastic, spread. So differing spread. There's also what is called homoskedastic, and homoskedastic means same spread. So a homoskedastic relationship would have a spread that is the same. This is actually what we want because we want the points to be about equal spread throughout, because we're going to be describing this relationship with a quantity known as correlation. And we want the correlation, which measures strength, to be about equal throughout the model. Because if it's differing, then it'll be stronger and then weaker, or weaker and then stronger. You may remember this condition from the plot doesn't thicken in Stat 201. We don't want to see that right here. We don't want to see outliers or maybe heteroskedasticity because the plot's getting thicker. These are all bad things which are going to pull away from a good, reasonable reflection of reality by using correlation right here. There are ways to fix this though. We can fix this with a transformation. Logs will pull in extreme values to where we have a heteroskedastic relationship right here. Well, we could pull it in a little bit and get a better spread. There is a little bit of outliers and only a little bit of heteroskedasticity now. Notice how it gets thinner. We want it to stay the same thickness throughout. We want it to be homoskedastic, same thickness. So over there on the right, we have a better relationship with minimum outliers and minimum heteroskedasticity. So I'd say it's pretty good, little outliers, little differing in plot strength. Overall, a lot better via the transformation of a log on the y variable. Let's go and check this out with some of the plots over here in R. So here we are looking at R right now, and let's take a look at the outlier demo. Now the reason we don't like outliers is because they can do anything. Now when using the outlier demo, make sure to go to View and Actual Size. You will need to use the actual size to actually be able to use this so it can find your points. Notice how we have a positive relationship here going upwards, and one outlier can make the relationship negative. So the black line right here is going through the black dots, and then the red line right here incorporates the red dot as part of the relationship. Notice how this only pulls it down a bit. The further away a point is, the more kind of gravitational pull it has, or more leverage in some instances, to pull the line down towards it. So these points right here have a lot of influence on the line itself and drastically change the relationship. This is why we don't like outliers. The new concept we'll be talking about here in this part of the video is Pearson's correlation. Pearson's correlation is known as the value of R. That's what you see right here in the corner, is the value of R for Pearson's correlation. And notice how it's 1 for a perfectly positive relationship. Well, all we need is one outlier to make it negative. Even if you try really hard, you can make it basically 0. It's kind of a game to see, can you get exactly 0? Oh, we got so close. And last try, here we go. Well, we tried. But notice now that one point is taking a perfect positive relationship and making it so it looks like there is no correlation. And you can do the same thing with a perfect negative correlation. Here's a perfect negative correlation. Oops, we didn't put that right perfectly in line. So it has to follow a perfect line, perfect negative correlation, and then one point is almost making it non-existent. Find that perfect spot right there, so close. But with this right here, we now have a relationship that virtually doesn't exist due to one outlier. So why don't we like outliers? They dominate the relationship in a correlation. Outliers can make a negative correlation positive, a positive correlation negative, a strong correlation weak, a weak correlation strong, a moderate correlation weak. Outliers can do anything. They dominate the relationship, so we don't like outliers. That's why we say QQ straight enough, no outliers, plot doesn't thicken. We do not want outliers in our correlation. So what you just saw right there was some demos talking about the values of correlation and how they are going to be impacted by outliers. So a correlation, to review again, is a specific type of association between two quantitative variables. So remember, associations are when we know one variable, it tells us something about another, and correlation means those two variables are quantitative. A lot of people in the real world just say, hey, gender is correlated with height. Not quite, because remember, gender is categorical, so it doesn't quite work. We in statistics know that the difference here is very important. Correlation has values between -1 and 1. -1 and 1 in terms of absolute value are the same. They're both 1, and they're perfect positive or perfect negative, meaning every dot would have to be perfectly on a line going up or down. The negative and positive indicate the direction. Now, the weakest value of correlation is 0. 0 is the least statistically significant, meaning 0 would have a p-value of 1, because it's purely random, and it would not follow any sort of linear relationship. So remember here, these are the values of correlation, -1 to 1, and the absolute value of the correlation is the strength of the correlation. So here is a really weak correlation, value of 0. There's no correlation right there because it's just random scatter. Now we have a moderately weak or kind of weak. The words are subjective, but it's definitely positive because it's positive 0.3. And here we have a moderately strong, moderate, negative correlation. And here is a moderately, or pretty strong, that's very strong. 1 is perfect, so that's really darn strong correlation right there, and it's positive, and all of these follow a line because you could put a line through them. So that's a strong, positive, linear correlation on the last one. The words strong or very strong are just subjective. We can get the value of 0.9, which is closer to 1, so it's much stronger. Now these are interesting. If you notice right here, which of these is the strongest? We might say they all have this. The value of r equals 0 means there's no linear correlation. The linear correlation or linear relationship does not exist. That does not mean there's not a relationship here, because this one, graphic 1, is the strongest. It has a perfect parabolic relationship. Look by the vertical scatter. It perfectly follows a parabola. So there is a perfect parabolic relationship with graph 1, and that is the strongest. Now, why does it have r equals 0? Because there is no linear strength through any of these. A flat line would go through those data sets. There's no linear relationship, and r only measures linear strength. So we cannot get the correlation here or get the strength of this with linear correlation properly analyzed. Once again, you saw the core demo just a moment ago. Check it out. You can put in some dots, see what kind of correlation you're getting, and see how outliers would impact that correlation. The R-squared is also given to us, and we're going to talk a bit more about this because this is a very important topic for practical significance. When it comes to practical significance, it's the do I care about it? So this is the hard one for people because do you care is going to be very subjective from person to person. So let's look at this example right here where maybe you're predicting stock prices and you find a correlation of 0.05. That's kind of like having an edge on Vegas. Because if you have that much knowledge about stocks, over the long run, you'll probably make a lot of money. R-squared is knowing X gets us blank percent of the way to knowing Y. So with whatever you know about the stock market, it gets you 5% of the way to predicting stock prices. Like you have 5% of the knowledge of what the stock prices will be. If you have an R-squared of 1, you would make perfect predictions if you could carry that over to new data. So imagine that if you could have 100% of the variation in the stock market understood from your model. I don't think anyone has that. But when is this important? Well, for stock, it'd be great to know at least 5%, but imagine you take all your earnings and open a parachute company. There's my best parachute right here. Now, what if I told you I only have 5% of the understanding of when parachutes open? You're probably not going to want to come to my parachute company if I only understand 5% of the variation in why my parachute's open. Doesn't sound good there. So the context of is an R-squared of 5% good depends on what we're talking about. It's always context with data. 5% of the stock market understood? Amazing. 5% of the variation in parachutes opening understood? Not so great. So how about this? We are trying to understand what another person rating a movie will rate a movie. We have movie rater A and movie rater B, and we look at the ratings. So 56% of the variation in movie rater B is explained by the variation in movie rater A. So write that down probably because that's a good thing to understand and be able to talk about. 56% of the variation in movie rater B is explained by the variation in movie rater A. Or you could say, knowing movie rater A's scores, you would understand 56% of the variation in movie rater B's scores. If it was perfect, all the dots would be on the line, and you'd be like, oh, if I know movie rater A's score, then I will 100% know movie rater B's score. Because it would look something like this, and you'd be able to perfectly say, and that is a 1-to-1 or correlation of 1. Even if it's negative, then you would still have an R squared of 1, because positive or negative wouldn't matter when we square the correlation. So if this was an R of -1, it would still be an R squared of 1, because you're squaring R to find out the coefficient of determination, which is R squared. And you'll probably never hear me say coefficient of determination again. Everyone refers to it as R squared, which is going to be the percent of variation in Y explained by the variation in X. Very important topic. So with this right here, let's go ahead and find some correlations. This is more of the classic way to find correlations. We're loading the data frame auto right there on the first line, and then we're using core_matrix for a correlation matrix. And the way it works is it does every pairwise correlation between them. The strongest correlation between this right now looks to be over, and I think I can find it right here. Nope, that's the second strongest because that's stronger. Remember, positive or negative doesn't matter when it comes to strength. It's just how close it is to the absolute value of 1. So 0.967 is the strongest from what I can see. We usually don't include values for strength that are 1 when they're on the diagonal, because that is the correlation between weight and weight. So something is 100% correlated with itself, or 1-to-1 correlation with itself. Not really interested when we're using X to explain X and Y are the same thing. So we just ignore the diagonal right there because it's the same variable. This is kind of the older way of doing it, but we have better ways of doing correlation with what is called all correlations. So think about what all correlations would do. All correlations would run for you all correlations. So when you run all correlations, you get all the correlations. So it takes a data frame, only looks at the quantitative variables, and tells you all the correlations between them. The names of the variables are var1 and var2, and then they're listed below right here, just in order, and it permutates all the combinations between them. Then you get the correlations and the p-values. But this is a little bit hard to read right now, so let's make it easier to read. We can add in the argument interest. Now, interest equals, and it has to be in quotes, the variable you want to think about. Now notice that we only see wins right here within the offense data set, and then the other variables right here. So this would be your Y, this would be your X, and then we have the correlations and the p-values. But we can do better. We can take this same code and add a sorted, and sorted equals strength is going to sort it by the strength. My favorite thing to see, or my favorite thing to do, is to do sorted magnitude, and you'll see that here in a second. So you'll notice that the strength of the correlation now goes from most negative to most positive, and look at these numbers right here. And you'll notice in the middle, you have kind of the weakest, which are closest to 0. I'll pen kind of jump there a little bit. There's the weakest, which would be this one right here is the weakest. It is closest to 0, and the closest to 0 is the weakest correlation. Let's go do a little more coding inside of R. Okay, so you notice right here we have a correlation matrix, and the correlation matrix says take survey 10 and give me columns 1 through 5. Now you might say, well, let's just do all of survey 10, and you get, whoa, you get a lot of output. No one's gonna read all that output. So that's why sometimes with this, we limit the rows, or columns, excuse me. So we could go here and do columns 5 through 11 and just get those columns right there to look at a correlation matrix of it. Now, correlation matrix are used a lot, and we'll just show that one correlation there by clearing the console, the one correlation matrix. It's still kind of a lot to kind of connect the dots on, but we're gonna go right here and use the same code and tell it, I want to do all the correlations for survey 10. I am interested in the variable GPA, and I want you to sort it by the magnitude, which is the absolute value of the correlation. So take a look right here. Now we have variable 2, which it sometimes switches the order of them, but we could still call that the Y variable of interest. And we have variable 1 weight, which is going to be the most correlated in terms of absolute value to it because it has the highest magnitude. Notice here, down here at the bottom, we have correlations closer to 0, and the p-value for this is actually 0.84. the p-value goes below 0.5 right about here. So this is where we have statistically significant correlations between GPA. Once again, these are scientific notations. Maybe I can delete off some of the decimals here and it might actually show it. There you go right there. Just remember, move the decimals when it comes to scientific notation. And as I said, this is 0.84 as a p-value. So that is a very high p-value, meaning the correlation between those two is likely by random chance. So this all correlations output is super important because it does all the correlations for us. So you can also use this to sort other ways, as we said, sort by strength. And now you can see we have the most negative correlation to the most positive with the weaker correlations right here in the center of the screen. Let's go back and look at a few more notes. We have what are called spurious correlations. A spurious correlation is one that really has no meaning to it. It just happened. You'd say, well, how is that possible? Well, things just happen sometimes by random chance. The world's weird. But there's also things called lurking variables. And we have ice cream sales and shark attacks. So if we say maybe ice cream sales explain shark attacks, people might think we're crazy. Or if shark attacks explain ice cream sales, they'll still think we're crazy. But maybe it's the temperature. And so the temperature outdoors is what we would call a Z variable. So that's a variable outside the XY paradigm because it's not within it. We call it lurking. So we also have things like how long people live and how many TVs they own. But probably wealth would be a lurking variable for that one because even though there is a relationship or correlation between life expectancy and TV ownership, it's probably it's probably not TV ownership. It's probably wealth that's the real variable behind that. And a lurking variable is the one outside of the XY relationship that is really the one driving it, or we think is driving it. But when we think about this, we have to remember that correlation does not mean causation. Causation will lead to correlation, like if one thing causes another, we will see correlation from that. But we cannot say that if things are correlated that we know one causes another, and we never say things are proven. We've got a lot of data to show this, and one of my favorite examples is Nicolas Cage. So Nicolas Cage has been connected to swimming pool accidents, and there's actually a positive correlation between the data of 0.666. So that sounds scary right there. So Nicolas Cage, knowing what he's done with the world, and the data shows it, no, we still need more Nicolas Cage movies. And this is a perfect example of a spurious correlation, one that is just happening for no real reason. It's just there. It's a spurious correlation. So those things happen, and they don't really have meaning to them. And probably if we collected more data, we would see that they don't really exist. So when it comes to lurking variables, we have ways of handling these. We can control for lurking variables by adding them to the model, and we will be getting more into this in future topics with regression coming up here in more lectures. But how can we test for correlation? When it comes to testing for correlation, we have ways of doing it with Pearson correlation and permutations. So here is a graphic showing you a relationship. Now we want to figure out if this relationship is by random chance or not by random chance. So we have to do what is called the permutation procedure. The permutation procedure is like if I took your tests, tossed them in the air, and then said pick up the nearest test near you. So if you did that, your time studying, which is quantitative, and your test grade would be completely random. That is permutating the results. So let's say we take an original data set, which has a relationship, a correlation of 0.94, and just mix it up. If you notice now, Y has been completely mixed up, like I tossed the tests in the air, and then they just landed on the ground, and then you see the new correlations. All of these correlations down there are created by random chance. Our correlation is 0.94. Now we plot our correlation and a correlation just as extreme, and then we figure out the probability of something just as extreme happening. And notice that there's very little just as extreme or more extreme than our result, meaning the p-value, which is the amount of shaded area outside the curve, is very small, i.e. 2%, which means we think our result is not by random chance. Low p-value means statistically significant, unlikely by random chance. If we had landed right here at the center, think what's here at the center. Now we didn't, but hypothetically, that would mean what we saw was a correlation of 0 in our result, and then everything would be as extreme or more extreme, and we'd have a p-value of 1. So there's good hypotheticals to think about, and think about what are small values of correlation likely by random chance, closer to 0, and what are large values of correlation unlikely by random chance, further away and towards -1 and 1. Now we need to make sure we're doing correlation appropriately. To do appropriate correlation, we need to make sure we meet the conditions of QQ straight enough, no outliers, plot doesn't thicken. But what do I mean by that? Well, first we need 2 quantitative variables. And that's pretty much always there, especially if you're doing correlation properly. Then we need a straight enough relationship, which means a straight line goes through it. Then we need no outliers. Notice how there's no outliers in that first plot. And then the plot needs to not thicken, which means it's homoscedastic. So it shouldn't be heteroscedastic. These have differing problems right here, like a spread that's thickening, like outliers, like maybe a little bit of nonlinearity, but mostly outliers with this one and plot thickening with the second one. So kind of identifying these things through the visual is what's going to be important to knowing when to use correlation. The associate command is something we've used throughout this lecture today. The associate command has multiple arguments we can input. First, we need to give it the formula format of y tilde x. Next, we need to tell what data frame those variables are inside of. The permutations are set to 500 by default, which means it will do 500 random throwings of the test scenario to see what would happen by random chance, and then putting those results into the histogram of permutations below. The seed can be used to control randomness, and we'll be doing this with some final examples coming up here in a second. Let's go ahead and take a look at the final results by doing one more test after this one. So in these results of the association procedure, you see the scatter plot with the border histograms. Notice how there is a mostly negative with few, not really any moderate, but very small, I wouldn't even call those outliers, they're just on the edge of the relationship. Got some border histograms showing you the center of the data, it's unimodal, and that's just for the univariate displays. Next, we have right here the permutation procedure. This is your observed correlation. Your observed correlation is about -0.39 or so. One just as extreme, that is not your observed correlation, but one just as extreme is 0.39. And so notice that none of the random results are outside of there. So what's interesting is we can actually estimate the p-value. Notice none of the random results are as extreme as your result. So since there's no results as extreme, the p-value is going to be estimated to be 0 for both of these. We'll talk about Spearman in another lecture. So the p-value will be estimated to be 0, and you see that right there with an estimated p-value of 0. I was a little bit off looking at the graphic. I said about -0.39, but pretty close still. Next, we get down here a confidence interval to estimate the true p-value. I am 95% confident the true p-value of this correlation is contained in the interval 0 to 0.007. So I'm pretty confident that it is statistically significant because it's completely below 0.05. That's what we need to care about, which is mentioned in the output here. We do not want to see 0.05 in the output. If we do, it's inconclusive, and we have to run more permutations to see if the interval is below 0.05 or it's above 0.05 to get a conclusive result. That's why the test is conclusive right here, because 0.05 is not in the interval. Last but not least, we can talk about the practical significance by taking the correlation value right here and squaring the value of correlation. Squaring the value of correlation would tell us 14.4% of the variation in wins is explained by fumbles. Notice up here at the top, we're using fumbles to explain wins, and about 14.4% of the variation in wins is explained by fumbles. Let's do one more example here using R. So for this last example right here, we have GPA and weight, where GPA is the Y variable of interest, and weight is the X variable, and the data comes from survey 10. We have a seed 320. Now, I want to point this out. When you run seed 320, look at the histogram. It's not changing. That's what a seed does for you, is it replicates the randomness. But if I remove the seed and run the code again, you'll notice the histograms are changing. The value of correlation won't change, but the p-value could change. Now, these results are pretty conclusive, so our p-value is not changing because the permutations are so far away from it. But with the seed, you get the same replication of results. So here we are with the same results. Now, is correlation appropriate or not appropriate here? Correlation is definitely not appropriate. Reason being is there are some extreme outliers down here. Down here in the bottom portion of the graphic, we have 1, 2, 3, 4, 5, 6, 7 outliers, it looks like. Actually, 8, I miscounted. At least 8 extreme outliers that could be drastically impacting this value of correlation. And still, it is statistically significant, and we are confident of that, but I probably wouldn't be using Pearson's R. We might start talking about another topic to use in another lecture. Thank you for your time, and make sure to email any questions or post your questions. We hope to hear from you, and have a great day.